The Moon, Earth's only natural satellite, orbits at an average distance of 384,400 kilometers, 238,900 miles, about 30 times Earth's diameter. Its orbital period, a lunar month, is synchronized with its rotation, causing the same side to always face Earth. The Moon's gravitational pull, along with the Sun's, is responsible for Earth's tides. With a mass equal to 1.2% of Earth's, the Moon is the largest and most massive satellite relative to its parent planet in the Solar System. It has a diameter of 3,474 kilometers, 2,159 miles, and surface gravity about 1/6 of Earth's. The Moon formed 4.51 billion years ago from debris after a collision with a Mars-sized body, Theia. The Moon's surface features lunar dust, mountains, craters, and dark maria formed by ancient lava flows. It is always illuminated by the Sun, except during lunar eclipses. The phases of the Moon are due to changes in sunlight as it orbits Earth. The Moon appears nearly the same size as the Sun, enabling total solar eclipses, and about 59% of its surface is visible from Earth. The Moon has profoundly influenced human culture, mythology, timekeeping, and science. It was the focus of early space exploration, with the Soviet Union's lunar missions and the US Apollo program. Apollo 11 landed humans on the Moon in 1969, followed by 6 more crewed missions. Robotic exploration continues, and crewed missions to the Moon are planned for the late 2020s. The common English name for Earth's natural satellite is simply Moon, capitalized. The term Moon originates from Old English mona, which, along with its Germanic counterparts, derives from Proto-Germanic *menon, which in turn comes from Proto-Indo-European *mensis, meaning month, related to the verb measure in terms of time. Occasionally, the term lunar is used in scientific contexts and especially in science fiction to distinguish Earth's moon from others. In poetry, lunar is often used to personify the Moon. Cynthia is another rare poetic name for the Moon, personified as a goddess, while Selene is the Greek goddess of the Moon. The adjective relating to the Moon in English is lunar, derived from the Latin *luna. Selenian, which is used less often, describes the Moon as a world, as opposed to just a celestial object. It comes from the Greek *selene, the word for the Moon, and its variant, selenic, is typically associated with the element selenium, although it was once used to refer to the Moon. The Greek goddess Artemis, known as Diana in Roman mythology, was sometimes associated with the Moon and was also called Cynthia after her birthplace on Mount Cynthus. These names, Luna, Cynthia, and Selene, are reflected in terms related to lunar orbits, such as Apollune, Pericynthian, and selenocentric. The astronomical symbol for the Moon is a crescent, as seen in expressions like M, meaning lunar mass. Natural history and formation isotope dating of lunar samples indicates that the Moon formed around 50 million years after the Solar System's formation. Several theories for its formation have been proposed, but none fully explains the Earth-Moon system's features. The fission theory, suggesting the Moon split off from Earth's crust, would require an unreasonably fast rotation rate of Earth. The capture theory, where the Moon was gravitationally captured, requires an implausible atmosphere to dissipate the Moon's energy. A co-formation theory, suggesting the Earth and Moon formed together, doesn't explain the Moon's metal depletion. The most widely accepted theory is that the Earth-Moon system formed from a giant impact by a Mars-sized body, Theia, with proto-Earth. This impact ejected debris that coalesced to form the Moon, just beyond Earth's Roche limit. This impact theory aligns with the angular momentum and mass of the Moon's core and is supported by computer simulations of similar events. However, newer models suggest that a larger portion of the Moon's mass may have come from proto-Earth rather than Theia. Despite these theories, some geochemical discrepancies remain. especially in the isotopic compositions of elements like zirconium, oxygen, and silicon. Simulations from 2022 indicated that remnants of Theia could still be present inside Earth, suggesting a more complex impact scenario. Natural development immediately after its formation, the Moon was much closer to Earth, making both bodies appear much larger in each other's sky. This proximity caused frequent eclipses and stronger tidal effects. Over time, due to tidal acceleration, the Moon's orbit has expanded, and its orbital period has lengthened. The Moon's surface has been shaped by large and small impacts, resulting in its varied landscape of craters. It was volcanically active until about 1.2 billion years ago, which led to the formation of the lunar Maria. Most of these basalts erupted during the Imbrian period, 3.3 to 3.7 billion years ago, though some are as young as 1.2 billion years. The distribution of mare basalts, primarily on the near side, remains a subject of study. The far side's lunar highlands, which are more abundant than on the near side, may be due to large impacts that made it easier for lava to reach the surface. Topological measurements show the near side's crust is thinner, which may explain the preferential flow of lava in that region. The Moon is a slightly elongated ellipsoid due to tidal forces and gravitational anomalies from impact basins. Its shape, known as the fossil bulge, suggests it solidified when it was closer to Earth. Size and mass: the Moon is the fifth largest natural satellite in the Solar System, with a diameter of about 3,500 kilometers, a mass 1/81st of Earth's, and a surface gravity of 0.1654 grams. It is the second densest planetary moon after Io. Structure: the Moon has a differentiated structure with a solid iron-rich inner core, a liquid outer core, and a partially molten boundary layer. Its crust is largely made of anorthosite, and its mantle is more iron-rich than Earth's. The Moon's small core is not fully understood but is likely composed of a metallic iron alloy with sulfur and nickel. Gravitational field: the Moon's gravitational field is irregular, influenced by mascons, positive gravitational anomalies, caused by dense basalts in impact basins, affecting spacecraft orbits. Magnetic field: the Moon lacks a global magnetic field, but has localized crustal magnetization, likely from an early dynamo that operated when the Moon was younger. Atmosphere: the Moon has an extremely thin atmosphere, almost a vacuum, with trace elements from the solar wind and radioactive decay. Water vapor is found in varying amounts, and a permanent dust cloud exists due to comet impacts. The Moon's atmosphere was thicker billions of years ago but was stripped away by solar wind. Radiation and temperature: the Moon experiences high radiation levels from cosmic rays, the Sun, and neutron radiation, about 2.6 times higher than on the International Space Station. Its axial tilt is very small, resulting in minimal seasonal variation in solar illumination. Temperatures range from 120 degrees Celsius in sunlight to 171 degrees Celsius in shadow, with some polar craters reaching temperatures as low as 26 K, 247 degrees Celsius, the coldest recorded in the Solar System. Surface and regolith: the Moon's surface is covered by regolith, a fine, impact-generated soil, with varying thickness depending on location. Below the regolith lies the megaregolith, a fractured bedrock. The extreme conditions make it unlikely for bacterial spores to survive on the Moon for more than one lunar orbit. Surface features: the Moon's topography has been studied using laser altimetry and stereo imagery. The largest topographic feature is the South Pole Aitken Basin, which spans about 2,240 kilometers, 1,390 miles, in diameter, making it the largest crater on the Moon and the second largest confirmed impact crater in the Solar System. The basin is 13 kilometers, 8.1 miles, deep, making its floor the lowest point on the Moon's surface. The highest elevations are found northeast of this basin, possibly due to the oblique impact that formed it. The Moon's surface has been shaped by significant tectonic activity, including shrinkage of around 90 meters, 300 feet, over the past billion years. Features such as fault scarps indicate that the Moon is gradually contracting as it loses heat. The Mare Frigoris Basin near the North Pole, once thought to be geologically inactive, has also shown signs of shifting and cracking. A lunar cave, identified near the Sea of Tranquility close to the Apollo 11 landing site, was discovered to be a collapsed lava tube. Measuring about 45 meters wide and 80 meters long, this cave offers a stable temperature of around 17 degrees Celsius, which could provide a protective environment for future astronauts from extreme temperatures, radiation, and micrometeorites. However, challenges like access and the risk of avalanches and cave-ins exist. This cave could serve as a potential location for lunar bases or emergency shelters. Volcanic features: the Moon's Maria, dark plains, which were once believed to be seas, are vast ancient basaltic lava plains. Although similar to Earth's basalts, lunar basalts have more iron and lack minerals altered by water. Most of these lava deposits filled impact basins, though the Moon's largest expanse of basalt, Oceanus Procellarum, doesn't correspond to a clear impact basin. Variations in surface albedo and flow margins indicate multiple episodes of lava flow. As the Maria cooled, contraction and cooling of the basalt created wrinkle ridges, low, sinuous ridges extending for hundreds of kilometers. These features often follow buried structures beneath the surface. The cooling also caused the formation of arcuate rills, concentric depressions along the edges of Maria. The Moon also has cryptomares, hidden mare deposits covered by ejecta from impacts. These older, obscured Maria are often more ancient than the exposed ones. Impact melt sheets, created by intense shock from collisions, can sometimes be distinguished from mare lava based on their texture and distribution. Sinuous rills are likely remnants of extinct lava channels or collapsed lava tubes. They often originate from volcanic vents and can be significantly longer, wider, and deeper than those on Earth, with uncommon features like sharp turns. The largest, such as Schroeter's Valley and Rima Hadley, are examples of such channels. Lunar volcanism has also altered impact craters. Some craters have been partially filled with mare material, and their floors raised or fractured due to uplift from beneath. Examples of this include Taruntius and Gassendi craters. Rare calderas, such as Hyginus, formed as volcanic collapse pits, smaller and shallower than typical impact craters. These volcanic craters are less common and typically lack the upturned rims characteristic of impact craters. The Moon's near-side Maria also contains shield volcanoes, volcanic domes, pyroclastic deposits, and scoria cones formed from high-viscosity lava. These regions represent ongoing volcanic activity, with some volcanic features being younger than previously thought. For example, a study in 2006 identified the Ina Depression in Lacus Felicitatus as being only around 2 million years old. Most of the Moon's Maria are located on the near side, covering 31% of its surface compared to just 2% on the far side. This distribution is likely due to a concentration of heat-producing elements under the crust on the near side, which cause the mantle beneath to partially melt and erupt. The majority of the Maria formed during the Imbrian period, about 3.3 to 3.7 billion years ago, though some of the youngest volcanic flows date back as recently as 1.2 billion years ago. Recent studies of lunar quakes and gas emissions suggest that lunar activity may be ongoing, with volcanic regions such as Lowell crater showing evidence of basaltic volcanism as recently as 2 to 10 million years ago. The lunar mantle may be warmer than previously believed, particularly on the near side, where radioactive elements have concentrated. The distribution of Maria on the near side of the Moon likely results from the significantly thicker crust of the far side's highlands. This may have been caused by a slow impact event from a second Earth-Moon, occurring a few tens of millions of years after the Moon's formation. Alternatively, it could be due to uneven tidal heating when the Moon was much closer to Earth. Impact craters. Impact cratering has significantly shaped the Moon's surface. Craters form when asteroids or comets collide with the lunar surface. It is estimated that around 300,000 craters larger than 1 kilometer are present on the Moon's near side. These craters vary in form, from simple bowl-shaped ones to complex craters with central peaks, terraced walls, and flat floors. Larger craters can form peak ring basins or multi-ring basins, which may have concentric rings. While most craters are circular, some have more polygonal shapes, possibly due to underlying faults. Some craters, like the Messier pair, are elongated, which can happen due to oblique impacts, binary asteroid collisions, or secondary impacts. The Moon's geologic history is marked by major impact events, particularly large multi-ring formations like Nectaris and Imbrium. These formations often serve as key markers in the lunar geologic timescale. Since the Moon lacks an atmosphere and recent geological activity, many craters are well preserved. Though not all multi-ring basins have been precisely dated, they offer valuable insight into the Moon's relative age. By counting the number of craters in a given area, scientists can estimate the surface's age, although secondary craters formed by ejecta can complicate this method. Radiometric dating of impact melted rocks, collected during the Apollo missions, suggests that most impact events occurred around 3.8 to 4.1 billion years ago, a time known as the Late Heavy Bombardment. More recent studies, such as those from the Lunar Reconnaissance Orbiter, have shown that the crater production rate is higher than previously thought, with secondary cratering affecting the regolith on short timescales. Lunar swirls are intriguing features that appear bright due to their high albedo and youthful optical properties. These sinuous, bright patterns are found in regions with strong magnetic fields and are often located at the antipodal points of major impacts. It's believed that these features are areas that have been partially shielded from the solar wind, which reduces space weathering. Presence of water ice is believed to exist on the Moon, particularly in permanently shadowed craters near the poles, potentially deposited by comet impacts or created through chemical reactions with solar wind. Missions like Chandrayaan-1 and LCROSS have provided evidence of water ice, though extracting it remains difficult. Earth-Moon system and orbit. The Moon orbits Earth at an average distance of 400,000 kilometers, taking 27.3 days to complete one orbit. It is tidally locked, always presenting the same face to Earth. Tidal forces from the Earth-Moon interaction cause the Moon to slowly recede from Earth at 3.8 centimeters per year, while Earth's rotation gradually slows. Over billions of years, Earth's rotation will eventually synchronize with the Moon's orbit. Lunar position and appearance. The Moon's position in the sky varies based on lunar phases and the time of year, staying above the horizon for 2 weeks at the poles. Its apparent size fluctuates due to its elliptical orbit, with a supermoon occurring when the Moon is closest to Earth, making it 14% larger and up to 30% brighter. Rotation and phenomena. The Moon's synchronous rotation means it always faces Earth, a result of tidal forces over billions of years. The Moon's surface is slightly brighter than asphalt, reflecting a brownish-gray light. It can appear red during a lunar eclipse or when low in the sky, and sometimes blue under specific atmospheric conditions. Eclipses occur when the Sun, Earth, and Moon align. Total solar eclipses will eventually cease due to the Moon's increasing distance from Earth. Eclipses and occultations. Eclipses, both solar and lunar, occur due to the alignment of the Sun, Earth, and Moon. The Saros cycle, an 18-year period, governs the recurrence of eclipses. The Moon also periodically blocks stars in a phenomenon called occultation, which is visible only from certain locations on Earth. Astronomy from the Moon. The Moon has long served as a valuable location for both astronomical and Earth observations. The Earth appears in the Moon's sky at an apparent size of 1 degree 48 to 2 degrees, which is 3 to 4 times the size of the Moon or Sun as seen from Earth, or about the width of 2 fingers at arm's length. Observations began as early as 1966, with the first images of Earth captured by Lunar Orbiter 1. A culturally significant photograph, Earthrise, was taken by Bill Anders of Apollo 8 in 1968. In April 1972, the Apollo 16 mission set up the Far Ultraviolet Camera, spectrograph, the first dedicated telescope on the Moon, capturing astronomical images and spectra. The Moon is considered an excellent site for telescopes due to its proximity and unique features. Certain craters near the poles remain permanently dark and cold, making them ideal for infrared telescopes. Radio telescopes placed on the far side of the Moon would be shielded from Earth's radio interference. Although lunar soil presents challenges for telescope components, it can be mixed with carbon nanotubes and epoxies to create mirrors up to 50 meters in diameter. A lunar zenith telescope can also be constructed inexpensively using ionic liquid. Living on the Moon. Human habitation on the Moon has been limited to brief stays, such as during the Apollo 17 mission. Astronauts faced challenges like sticky lunar dust, which had a gunpowder-like smell and raised health concerns. In 2019, a plant sprouted on the Chang'e 4 lander, part of a lunar micro-ecosystem experiment. Legal status: no nation claims ownership of the Moon, and the 1967 Outer Space Treaty designates it as the province of all mankind, restricting its use to peaceful purposes. The 1979 Moon Agreement prohibits resource exploitation by a single nation. However, the US and others, through the Artemis Accords, challenged parts of this agreement. As interest in lunar exploration grows, there have been proposals to preserve historic landing sites and grant the Moon legal protections, similar to those for natural resources on Earth. Coordination and regulation: as human activity on the Moon increases, there is a push for better coordination and international regulation. Current lunar programs, like the US-led Artemis program and China's International Lunar Research Station, involve multilateral cooperation. Organizations such as the International Lunar Exploration Working Group aim to promote collaboration. Crescent symbolism: the crescent has been a symbol of the Moon since ancient times, appearing in various cultures and languages. It has represented lunar deities and is central to the star and crescent symbol, which has historical and religious significance. In modern times, the Moon continues to inspire cultural and legal debates, particularly regarding space exploration and the ethical implications of lunar resource use. Lunar effect: the lunar effect is the unproven belief that the Moon's phases influence human behavior and physiology, with terms like lunacy originating from this association. Ancient philosophers like Aristotle and Pliny the Elder suggested the Moon's gravity could affect the brain. However, studies have disproven these claims, showing no significant link between the lunar cycle and behavior, such as hospital admissions or traffic accidents.